Well, thank you all for joining us. I'm hoping that a lot of you will be rewatching this session because I can guarantee it's going to be a good one. This Lunch and Learn is about concurrency in Golang, powering efficient microservices. Whilst that sounds like gobbledygook to me, it's all about basically utilizing Golang, the language, for making simple tasks more effective. Basically, that's how I put it in language that I can understand. And we want to thank you so much, Oluyemi, for hosting this. I'm so excited for this presentation, and I'll just hand over to you.
Thank you, Alex. All right, I will just go ahead and share my screen.
Brilliant.
You're gonna see yourself for a minute. And okay, all right, here we go. I hope
Fabulous,
you
we
can all
got
see
you.
my screen.
Yeah.
Perfect.
Cool. Slideshow. Here we go. Okay, for those who will be watching this, thanks for joining and taking your time to listen to these and also learn from me too as well. I will just focus on a specific feature today in this programming language, Golang. Like Alex said, this is concurrency in Golang. Um, the wide adoption of Golang, to be honest, is actually primarily because of concurrency. This is a feature that is really available. It's not really particular to just Golang. It's something that it's been around for a long time. But then Golang does it in a special way that makes it easier for you to build microservices or even cloud native technologies apps or anything you want to build with it. As we'll dive deep into it, I will just mention a few things. Of course, this launch and learn session, it's not going to give you from beginning to advanced. But I'm hoping that from beginning to some sort of somewhat intermediate and then a foundation that we can build on. So what we will cover here is take a look at what concurrency is. You'll be surprised that it's really simple. It's just something you do every day. And then, but we're just going to look at it from a programmatic kind of perspective. And then why you need concurrency in your APIs or microservices. And take a look a little bit about concurrency and parallelism because people tend to get this confused a lot. There is a bit of similar kind of process between both of them. They are not exactly the same. And then how Golang handles concurrency. Take a look at a bit of patterns, maybe pitfalls and best practices, and then we conclude on those. Who am I? Again, my name is Oluyemi Olushuse. I'm a senior software engineer. I volunteer here for a particular project, which happens to be a dev lead, and we're very close to delivering, making progress on those. And also, I'm a fitness enthusiast. I love football. If you're watching this and you're a Manchester United fan, hello. Um, Closest to that is I love music. So, what is concurrency really? Have you ever been in a situation when you're trying to make a cup of coffee and toast the bread? These processes, you're carrying them out, independently, and then none of them is really stopping each other, and you're able to complete it without one blocking another. That's concurrency. As a matter of fact, we could say we're done with this presentation today because this is something that we basically do every day. So I can see the smile on your face, Alex. That means you're feeling like a programmer right now.
You've made it relatable. I'm loving this already, literally.
So cool. But then we'll go ahead. It's more like one of the most efficient feature of Golang, like I mentioned, and it's just a different way for you to carry out different tasks without one blocking each other. And then as we go on, take a look at some of the primitives and some of the features that you need and how to structure it. I'll be switching between a code snippet and also the slide. So what exactly is concurrency? I gave a few, just a preview earlier talking about a relatable task, making a cup of coffee and toasting bread. Take a look at this as you trying to do this, boiling your water, getting your cup of coffee ready, brewing the coffee, making the toast. You are doing all of this effectively, and then you're getting result, multiple tasks carried out by you, and then getting it done. So relate this to an environment where you have a lot of requests coming into your platform, tons of requests hitting your microservices at the same time. Ability for you to structure your program in a way that can handle all of these tasks without one blocking another is what concurrency is. In simple terms, multiple tasks at once, even without running them simultaneously. I mean, even if they're running simultaneously, but then they're just not blocking each other. Parallelism is just a way of saying all of them are handled differently. I'll just show us something from the code, which I think, every programmer tends to love. Take a look at. Um, a simple function here is make a cup of coffee and toast bread. Can I confirm that you guys can see the screen? Is it big enough? Cool.
This is great.
Cool. This is actually for concurrent execution, but this is just a sequential one. Now, if I run this, now running this, you can see the sequential step, making coffee one, down to four, toast the bread, one, down to four. So picture this as four people, trying to make coffee and toast bread at the same time. So if they are doing this sequentially, one person will have to complete making coffee, irrespective of how simple the process might be. Maybe you're using a coffee machine or you're trying to boil the water yourself. But then they have to be done before going to toast the bread. Now, this might sound like, well, it's just four, but picture when you have thousands of requests coming into your platform, and then you have to handle different processes. You wouldn't want to be this because this is not really efficient. You want a process that can actually be carried out concurrently, without blocking each other. Now, turning a sequential process to a concurrent one using goroutine. I will get to goroutine to explain further, but basically, goroutine is just the magic here. It's just a way of saying, I want to carry out different processes, but then run them in the background separately instead of just running them sequentially. Now, take a look at what we had. We have this coffee and toast spread. It's as simple as it can get. But then when you bring in concurrency to this, I'm just going to comment this out temporarily. I'm going to take this time out as well. And if we run this code now, again, first, we didn't say we get no result. This can be scary, like what just happened here. As I will go deeper into this later, but just a little bit of intro about this Go routine is you have a main function, which is the main routine in your project. It is the entry point to every microservice or any application that you build with Golang. Now with this, it runs, begins a process, and then completes the process because at this point, with Go Make Coffee, you're actually spinning up a different Go routine entirely. So it's going to keep running, but then there's nothing to really communicate back to the main function to say, you know what, this is done and it's returning a response. Because of this is going to terminate and then end. So all this delay that I had here is just to say, okay, you know what, just wait for 2 seconds before you time out so that I can get result back from those. In a real world application in a production environment, you will not want to do this. So there's a different way to undo that concurrent process of allowing other Go routine to complete. But just for now, I'm just going to introduce that. And you can see that this changed a little bit. What you're getting is you're toasting bread one, making coffee two. And there is no guarantee to say one process will start first. It depends on how fast or the computation that is involved in your program. Whichever one is done, you're going to see the result first. Even if we run it again, you're going to see something different. It might be the same, it might not be. So every time you run it, you're getting a different kind of flow and value. Now, this is a bit better than just having sequential process because with this, you're guaranteed that you're going to get the result done completely at the end of the day. Going back to the slide, when do you actually need concurrency? Like we've just given an analogy about multiple independent tasks like toasting a bread and making coffee at the same time. If you have your microservices that requires making a lot of API calls, or you have tons of background processes running at the same time, like sending email, caching data, or retrieving data from the database, or you need something that is really event driven, like a real-time responsiveness, or you need to update a dashboard dynamically, right? If you have actually been building for some time, you're going to start finding some of this relatable as a process that you need to kind of optimize. Then at that point, you want to bring in concurrency. As we've just demoed here, you see how concurrency is just being introduced by just adding this keyword. The same thing here. If you have a simple program like this, just to say, you know, hello, is as simple as it can be. But then at the end of the day, if some of these processes are not really optimized, your results might either be delayed or it might affect the performance of your project. Cool. So you need concurrency when you notice that your program is actually beginning to grow and you're thinking about scalability, you're thinking about performance, and then you want to think about responsiveness and how to execute those tasks effectively. Then you need to start bringing concurrency in. So earlier I talked about concurrency, and I think I mentioned parallelism too as well. So the main distinction between this is, for concurrency, if you're making coffee, you're toasting the bread, you're doing something, you're starting, you're pausing, and then you're resuming. So it's entirely efficient because you're not waiting for one to complete before going to another one. In most modern laptops or production environments now, you have operating systems with tons of core, maybe like 7 core, 5 core. Really, all this core means you have um, a program that can execute instructions separately on different cores, right? You could say you have a very good number of cores that can handle tons of requests. But by the time your application start to grow, imagine getting thousands of requests. Those calls are going to be overwhelmed eventually. And then this might actually crash the system. So it's really resource intensive because you might need to then scale your resources, or on a specific day, we're expecting thousands of sales, for example, on an e-commerce platform, then you want to start thinking about let's go bigger so that we can handle more. But concurrency, it's entirely handled by the go runtime. So you don't need more like a very huge resource. You can use a single core to handle that. And then these tasks are carried out. You do this, stop, continue, then go back to it, depending on the computation. So that's the decision between concurrency and parallelism. Both of them are completing tasks, but one is running multiple tasks at the same time, switching between them. And then one has to focus on one. Take a look at this toasting and coffee thing, for example. If you feel like you have four people, four of them who needs to toast the bread, you could bring four different machines for them to toast, right? This is just, okay, everyone, you have one. But then is that sustainable? Or what if you have 1,000? Are you going to then go ahead and get four different toaster machines? So those are more like really relatable examples. And if we take a look at, I've got a couple of code snippets, so I can still show us what running um, concurrently looks like. Um, so we've just had this look at about this sequential, and then a different one about, setting it up to run concurrently. I would like to go to like something about race condition, but just before that, let me just give a basic intro to that. So little deep dive into goroutines again. This is very key. An understanding of goroutine is key for you to even be able to expand on the implementations that you want to handle. So, like I said earlier, it's just a lightweight thread. It's managed by Go runtime. It's not entirely tied to the resources of your whole operating system. It's basically just something that you can spin up. And then once your program terminates, it's going to end as well. You can handle millions of them, efficiently, at the same time. Now take a look at channel. I think Go routine is good. You've got a question. You got a hand up.
I do,
I like.
thank you. And sorry, because this is probably a basic question, but I was wondering if you could explain what a thread is. Is that just a form of code or?
Good question. So a thread is the best way to kind of put it is understanding how your code are being executed one line after another. So if you have, um, for example, an algorithm that is supposed to check a user in the database, and then if they exist, you're going to pull that data and then you're going to change their first name or their last name, right? You could have that in different lines. So a thread will go through one line after the other. Just like we have this function here, um, here we have this make coffee and toast bread. And the sequential execution is going to go with make coffee first. There is nothing you can do, but make coffee is the first on the line. So it's going to execute that thread. And then once it's done, it then goes to toast bread. That's why from the output earlier, we were able to say make coffee one, two, three, four. So that's what thread is all about. But then what Go routine tend to do is spin up different thread. So instead of just waiting for this to be done and going to the next one, having a Go routine is just going to spin up based on what you have. We're saying, you know what, make a cup of coffee. We're saying five. So it's going to spin up different number of Go routine for that. So you can have tons of threads spread out. And then all those are, they're not really, like I said, not really resource intensive. They're just lightweight. And then bringing that all back, you can collate all the results and then put it together and you get a basic output. Does
Amazing.
that make
Thank
sense?
you. Yeah, that's brilliant. Thanks.
Awesome. So we've just talked about how you can spin up different Go routines aside your main routine. But then there are times when you need to send data between those because they need to communicate with each other. How do you kind of enable the safe communication between them? Two of the main highlight of this session today is for us to touch on Go routines and channel, because these are the major primitives that will actually help you build a concurrent program in Golang. So channel is just a way to communicate. Imagine you have two people. One is maybe toasting bread, and another one is receiving it and then giving it out to people. That's that's some sort of channel between them. Right. Now, if this number kind of increase, you know that once this is a sender and this is a receiver, so someone gets generate the result, another one takes the output, and then give it out, output it, or send it as a mail, or things like that. And then how do you create channel? I will let the code speak here too as well. I will just show us what channels look like and how to create them for the benefit of those who will be watching later too as well. And now, so you have a Go routine. I already showed us what a Go routine looks like. It's all about adding these two keywords, really. It's as simple as that. Just go to your function, and then doing that will spin up a separate Go routine. And this way, you create a channel by just saying make chan. As a matter of fact, your CH could be anything, you want it to be. It doesn't have to be CH, but CH just seems to be more like a standardized approach to it. But if you want something descriptive, you can also change that. So this make chan just kind of creates more like a buffer that holds your channel and say, okay, by the time you want to allocate data into this, we have something for you already. So you create that. And then the type is, we're saying the data type should be string. If right here, I'm trying to send a number to this channel, of course, I'm going to get an error already. And then, looking at the error saying cannot use 5 because this is an hint. And then what I was trying to send as defined here as a string. So this way, if I have tons of Go routines here, spinning them up with this channel, each one can actually send something to the channel and another one can actually listen to it. Um, the the syntax is when you're sending data to the channel, you define it with this arrow. And then if you're going to get data out of that channel, so the arrow is just the other way is inverted, and then there's no space in between it. So in this case, we want whatever is sent to this channel from that Go routine to be printed to the terminal. That's where you have from the print line. And if I switch to that, we are definitely bound to see what the result will be, which will be the task complete on that. Yeah. So task complete. We're going to see this in practice when we check these microservices, but this is just an intro to it. Creating a channel is as simple as a way of saying, even though these processes don't know about each other, that's why you can have make coffee starting first and then toast following it. But if we need them to communicate, one of them will have to output the data and the other one will have to receive it. And the best way for Go routine to communicate in a concurrent program is through channels. And I think it's also worth noting that once you open the channel, you're also supposed to close it because once you leave it open, you just kind of, it's more like you're opening the resource. You're saying this channel is open. You know, you have a sender and the receiver, and I'm saying there's a channel open. The receiver is going to keep waiting. Like you said, the channel is open. That means I can get data from you. When are you going to send that data? And if you're not sending the data, you're leaving the receiver hanging. So that program is going to throw an error eventually. And you're going to say like, okay, this data is not coming back when it's supposed to. As part of some of the primitives for ensuring proper communication between, in a concurrent program between Go routines is wait group. Wait group is just a way of saying, how many Go routines do I have running at a point in time? And once those start running, how can I ensure that my main routine is going to stop, is going to wait for the entire execution before it So earlier when we started, when we ran this program, where I can even use a simple one, when we ran this program without this, you realize that there was no data printed to the terminal. Let's say that again in action. Or me.go. Nothing comes out because this main routine started and that there's no way to communicate and say, okay, hey, I'm still running. Could you wait for me to be done before you end your execution? So, but we introduced just a temporary delay here to kind of simulate that. Wait group does this in a way that it communicates to the main Go routine to say there are tons of Go routines, separate Go routines spun up on the ground that are run in the background. So you'll have to wait for those to be run before you can actually exit. Um, these find a way to kind of avoid things like race conditions. So race condition is another term that is just used to explain multiple go routine trying to access a shared data. And then if one is trying to get data and the other one is trying to delete or consume that data, then it becomes a problem because there will be lack of consistency between which one is getting hold of that first. With the code, let's take a look at race condition. Now take a look at this simple function here to say increment. By now we're familiar with Go, meaning this is going to be a Go routine. Now this counter, once you run this program, you're saying run 10 times. That means it's going to spin up 10 different Go routines. And by the time those ones start, what you're just trying to say is you're going to start with zero, but keep increasing the counter, which is the zero. It's more like a global variable here. It's initialized with zero. So that means it's going to start from zero until it get to 10. So ideally, we're supposed to see an output that says 10 in the terminal. If I run this now, I'm just trying to use this to bring to life the concept of race conditions and how to use weight group to then address those. So if I run this now, oops, okay, here we go. I'll go routine slip. Wonder why that happened. All right, I'm a terrible actor. That was intentional. So now that we have that, I think I should even still leave that open so that we can see what it is. This kind of introduced a very interesting error. This is something that I've learned in the hard way to fix because this program is still simple. And then if you don't understand the basics, it becomes very, very tedious to handle a large program. So what is going on here? I mentioned about wait group as a way to tell your main go routine to say, I have 10 go routine running, and I'm going to keep increasing the counter. So WG here is somewhat more like a counter to track the number of go routines that you have. Now, right now, within this loop, we're saying increase it by one. You can say WG.add. Now it's going to increase the counter by one. And instead of us using time to say delay, we're using wait. This is also a different function that you can call to say main go routine, please wait for all other routines to be completed before you can actually time out. So, but here we're saying increase by one. That means WG is going to be one. But WG.wait would only run when your WG is zero. So meaning that we need to find a way to decrease this value. And we are not doing that yet. And that's why there's a deadlock. So deadlock is just that term that say all go routine has sleep because you're not telling us which one is active or not. All of them are just still running. So to fix that, this is just a syntax. I'm going to bring this up. All of these are quite important to build the basics to how you can actually structure your microservices to handle concurrent programs. Now with this, we're saying WG.add, increase it. But we're saying decrease the value. And the defer keyword is just saying after the entire program, please defer this. So when the programs are completed, then you can run it. Now, if we run this program, now we're seeing a final counter of 10. Happy days, but then not entirely because it could be inconsistent. Now it's 8, you know. We're expecting 10, but we got 10, so we can as well feel like, oh, this program is good to go, but not. And the reason for that is the concept of race conditions, because there's a shared data here. I do have a function that is mutating a global variable counter. Now, when this loop first one is run for the first time, it's going to increase it to one. Going the second time is going to increase it to two. But we're not certain which of the go routine is actually increasing it. So this way, they are not consistent. So whichever result is actually being outputted before the main routine exits, that's what you're going to see. That's the result you're going to see. That's why it can actually be entirely. Now we're getting 9. At some point, we might even get 6 or 4. So this is in no way consistent. And that's where solutions like synchronization, that's why wait group and synchronization here. Now, wait group solves the problem of telling the main go routine to say, wait for the entire all other go routines to be completed before you exit. But then synchronization needs to say, there is a shared data going on. We all need to access this data. But then how do I tell if one particular function or one particular go routine is done with that data so that another one can hold it? Think of it when you're trying to, I mean, 5 people are trying to make coffee and then toast bread, right? If one person is making coffee, 2 people cannot do it at the same time. So I need a way to communicate by saying, I'm making a coffee. Can you hold on? Once I'm done, then you go ahead and do that. Or I'm toasting the bread. Can you hold on? Once I'm done, then you go ahead and do that. So one person can be toasting, making coffee. And once we're done, we're going to swap because that way we're controlling the entire flow and the process. Now, doing this is by using mutex. Now, I have it here. So it's just saying lock. And then once I'm done, unlock. So in simple terms, I'm holding on to this data. I'm not going to let it go until I'm done changing the data. And once I'm done, I let it go. So take a look at this function and look at it being run by 10 different people. So 10 different loops. That means one is going to go ahead, increase the counter. And once it's done, it's going to unlock. It's just that this is very fast. This program runs very fast. So you're not even going to notice like how many seconds or milliseconds did you take to do that. And that's one good thing about, automations. And now with this, if we run this program, no matter how many times you do this, you're going to get 10. You're going to get 10. Because this way, each go routine is doing what it's supposed to do. You start with 1, The second one increase it to two, increase it to three. So this stays consistent. And I'm going to give us an analogy, something that we are quite familiar with. And then sometimes you might even notice and feel like, how did this work? Because if you're not a programmer or you don't know the background or inner workings of things, you probably don't want to bother about it. But this solves the problem of sharing data and then how it's been handled so that you can synchronize the value. Now, take a look at this worst scenario. Like your bank account at the moment is, say, £200, and then you want to make an online purchase of 100, and then a friend is going to transfer 500 into your account. Now, there could be a problem with what will you say as your balance at that point in time? Because with 200 in your account, an online purchase, you have no idea when all of these processes are going to make that call to your bank account. I mean, the banks definitely have microservices built to handle credit and debit. So if credit is going to make a call, the shared data here is your account balance. Now, if credit service is going to make changes to your balance, it needs to hold on to that. So maybe at some point, if your purchase goes in first, that means the debit will happen first. You should see 100 as balance because that's been debited. But if credit goes first, then you should see 700 even before initiating the call to make the purchase. So this is something that it's quite I think there was a time I noticed that I saw a particular balance. I'm like, where did this come from? I had no idea that I didn't get a notification on time that there was a credit to my account, but I was going to make a purchase. So with this, a way to kind of put a mechanism that can control consistency, concurrent program will then make it easier for you to see. I mean, for example, financial details like it. That's why most fintechs now, think of banks like Monzo, Revolut, most of these guys use Golang as a major stack. And that's because of the concurrency feature in this, because you can imagine the tons, millions of customers that they have. And then all these transactions happen daily. You can have 1,000 requests per second. If you don't have the programmer sufficient enough to handle this, then it's going to be a problem. People are going to be calling that I can see 20,000 balance, but now I can't spend it. I don't know how that happened. So consistency is quite key in a program like this. A shared data, you find a way to kind of undo that. And that's where mutex, this MU is actually mutex, and mutex is just mutual exclusion, ensure that only one service modifies the balance at a time. So why is concurrency really important for microservices? I feel like with some of the points that I've mentioned, we can begin to think about, oh, this is really crucial already because, you want to handle multiple requests at a time and you have calls to your database, API calls, query the DB, and maybe send an email to as well. It's always good when you do carry out a particular transactions and then you get, oh, successful immediately. But in the background, there's a lot going on. Something is trying to send you notifications, trying to send you an email, they're trying to debit your account. But of course, you don't care about that for as long as you can see that, okay, this is updated, And then most of this, there's a lot that goes on into the backend architecture of all of this flow. And concurrency, like I said, nothing is blocking. It enables non-blocking execution. If I just switch to a particular microservice, I have this here to just kind of demonstrate. I think we've seen this sequentially, but then this one is making a call to a particular service. And if we also run this, you can see this happen one, then followed by the second one. So it's not entirely concurrent. But then if you look at the concurrent version of it, all we are doing is we're saying, okay, I introduced channel earlier and I talked about, what to create a channel. Now you have a channel for the first one to fetch the data. You have a channel for the second one, and they're going to send back a particular response. So once you go into this function, it makes that call to the API. If there's error, it returns the error. If not, it goes ahead and then send the response to the channel. Now the response is being outputted to a different variable result, and then these have been printed to the terminal. So if I move in into microservice concurrent and then run that as well, the result is very fast. And I think in the second one it coming, I'm going to compare the time it took to complete one service being returned to the second one. I think we're nearly there to the end of it. So every gateway service handle multiple API requests call concurrently instead of sequentially, which kind of improve performance as well. So the key takeaway is for your microservices to be extremely scalable and responsive to as well, you need to bring in concurrency. And I dare say, use Golang, you know, to be with as well. Um, but before conclusions and all that, I'm also going to show us how this work. We've seen the result already, but just comparing what result look like if you run a terminal. I mean, if you run a program, um, an API called microservices sequentially and also concurrently. Let's see what the result looks like. Split terminal. There we go. Now, if I go to API gateway and concurrent, okay, good. Run this program. Okay, so this is 144 milliseconds, right? 146. At least not entirely bad, but in a production environment, this delay will increase because there's network connections and there might be internet issues. There may be retrieving data from the database. There might be making some sort of extra API calls. But compared to when you run this in a concurrent environment, you can see 94 milliseconds. It's still the same API, is the same endpoint that we're calling. But with this, you can see some sort of improvement, no matter how much it might even get better. You can see it keep reducing over time, but then this will keep increasing. So these kind of demonstrate how efficient it is to introduce concurrency into your microservices, because this way you are certain that you can handle things like consistency, you can easily scale, you can handle thousands of requests. This is one of the reasons why Golang is actually being adopted a lot, for cloud services. Everyone is moving to the cloud now. Even banks are beginning to adopt, cloud technologies. They seems to be very conservative when it comes to their data, and then they want to run everything in their own database. I mean, their own data center, have a server separately, but now everyone is then trying to adopt the cloud. So that means fast response and improved performance too as well. So with this, the key takeaway is concurrency powers scalable and the responsible microservices, responsive. And then Go routines enable lightweight, efficient multitasking. You can spin up tons of Go routines to carry out the same process on a particular data. But how you handle the shared data and safe communication between all of those Go routines depends on how you control it. And of course, synchronization, as we've seen, as we saw earlier, cannot prevent race conditions or deadlock. So if a program or a particular microservices doesn't need to scale, or you're not expecting a lot of requests, ideally you will want to stay away from, optimizing performance by using concurrency, because obviously it can introduce a lot of complexity. And if you're not really familiar with the basics, it might be, you know, um, you might come up with a lot of issues, and then maybe a tall order to kind of, resolve all that. But really, it's all about using it wisely. Thank you. I think that concludes my presentation for today.
Wow, thank you so much. Honestly.